Hello students, welcome to our course Environmental Modeling and Simulation. Today in this lecture we are going to continue our discussion on environmental non-reactive and reactive processes. In the previous lecture we ended at a discussion of simple reaction where the reactant A transformed into B, and there is both the forward reaction and the backward reaction, and we looked at how to define chemical equilibrium and the equilibrium constant. This can be generalized to any chemical reaction. For example, let us say we have A plus B, forward reaction, backward reaction C plus D. And the stoichiometric coefficients, let them be small letter A, B, C and D. So, for a generalized equation like this, the forward reaction would be proportional to the product of the reactants. So, concentration of A, again the square brackets indicate molarity, raised to the power of the stoichiometric coefficients. This proportionality we can add proportionality constant. So, the rate of forward reaction will be given by Kf, which is the constant for the forward reaction. Similarly, the rate of backward reaction will be proportional to product of the products to raise to the power of the stoichiometric coefficients. So, we have two products here C and D. The molarity of C and D multiplied raised to the power of corresponding stoichiometric coefficients C and D. Now, again we can introduce a proportionality constant. So, then we will have the backward reaction rate is equal to Kb C to the power small letter c, d to the power small letter d. Now, at equilibrium what happens? At equilibrium, the rate of forward reaction will be equal to the rate of backward reaction as we had discussed. So, there will be no net change in the concentration of A and B and C and D. So, basically the concentrations of A, B, C, D will become constants. So, we can say that Kf, so this is forward reaction from here. So, these two will become equal. This is backward reaction coming from here. So, now what we can do is, since A, B, C, D are constants, we can bring them on one side, and Kf, Kb of course are proportionality constants. So, what we get in this case is Kf by Kb is equal to products of the reaction raised to the power of their stoichiometric coefficients divided by product of reactants raised to the power of stoichiometric coefficient will be equal to ratio of the forward and backward reaction proportionality constants, and this can be described as the new constant, which is the equilibrium constant. When we were going through the ordinary differential equations and learning how to write simple ordinary differential equation 1D and 2D for chemical reactions, we looked at autocatalysis. And in case of autocatalysis, what we found was that we use similar principles for writing the rate of forward reaction, backward reaction, and if needed for writing the equation corresponding to the equilibrium constant. And of course, this can be generalized to most of the reactions. Now, let us take a look at a special case. Again, this is a case of catalysis. So, let us look at a case where we have, of course, this is enzyme mediated. So, we have an enzyme E and then we have the substrate S. And as they move forward, as they react, the enzyme and the substrate, they form a complex. Let's call it ES complex, which further breaks down into enzyme. So, enzyme is released back. Of course, this is a case of catalysis. It's an enzyme is a catalyst, and then we have the product. Now, this is a typical scenario that we see in wastewater treatment in case of many microbial activities. Why is it important in case of microbial activities, like what happens in activated sludge processes in aeration tank? Because in order to degrade the substrate, in order to degrade their food, most bacteria will use varied array of enzymes. So, most of the biodegradation, bioremediation, consumption, biouptake processes are enzyme mediated, and all of those reactions in general would resemble something like what's written here. Now, in this case, The question is, what is the rate at which the product, P is the product. Let me write down the names. E is the enzyme and S is the substrate. Now, we are interested in the rate at which the product is being formed. Of course, we can write the ordinary differential equations for this, and people have written it, people have solved it, and it simply boils down to this: dp by dt is equal to U max, which is related to the maximum growth rate of bacteria or microbes that we are looking into, multiplication of product and substrate concentration divided by Km plus S. Now let's look at this. Mu max is maximum growth rate of the product. Km is a constant, and we'll see very soon what is the relevance of this constant. So we see that this is how dp by dt looks like after you have written the ODEs, after you have solved it. Now, of course, if we know the mu max and we know the Km, by looking at the ratio of product and substrate at any given time, we can estimate the rate at which the product is being formed. Now, this is a very simple generalization of enzyme mediated reactions. So, just to clarify, in the previous slide, we looked at chemical reactions where the reactants come together and form the products. What we are looking right now at are enzyme mediated reactions, which are slightly different, which are quite different actually from the one we saw in the previous slide. Now, this equation that we have here is very simple, very useful, and it's widely taught in undergraduate classes of chemical engineering, civil engineering, environmental engineering, and other allied sciences when we talk about wastewater treatment. However, this is still a non-linear system, a non-linear equation. So, if you're adding it to your ODE, for example, let's say you have the rate at which product is changing is equal to Q in, C in. So, basically rate at which things are flowing in, Q out, C out, and then you have this dp by dt. So, you have volume dp by dt due to enzyme mediated reactions. So, this is dp due to enzyme mediated reactions. If you write your system like this part is still nonlinear, and if you remember from our previous lectures, we have established that nonlinear systems are very, very complicated, very hard. So, under two circumstances, when this part becomes linear, this equation is, this particular part, the enzyme mediated reaction rate, is very easy to incorporate into our ODEs. So, what are those two situations? Let's take a look at that. First situation is when your substrate concentration is very, very low. So, when S molarity is much, much lower than Km. Now, again, I told you we look at the importance of Km. If your substrate is very, very low, is less than Km, then it becomes approximately, you can write this as dp by dt is approximately equal to mu max into product concentration into S concentration. Okay. Now, in the second scenario, which is second order, by the way, before I move to the second scenario, this is a second order reaction. So, it is still not a linear system, but it is easier to solve, easier to integrate, or to do geometric analyses on. The second scenario, this is the first one, the second scenario where this equation becomes linear is when your substrate is much, much higher than Km. So, if your substrate is much higher than Km, you can ignore the Km, and then the substrate will cancel, and you will get dp by dt is equal to mu max into product P. Now, you have a linear system, first order decay or first order increase or decay, whatever the sign is, whether the reaction is reducing or increasing. Well, in this case, it's increasing, so plus. So, first order growth of product. In these two cases, our dp by dt becomes more easily solvable. Okay. Alrighty. Now, I want to summarize enzyme mediated reactions, zero first and second order reactions. So, this is basically a revision of what you have studied already in, hopefully in your undergrad and even before in your 11th, 12th. But I have noticed over the years of teaching, it's always a good idea to revise this. So coming back to our reactive processes, we have simple chemical reactions where reactants react with each other and form products. Equilibrium constants are easy to write, as I showed today in the lecture. Then we have the second class of reactions where there are enzymes mediating the reaction, in which case we saw this very simple generalized equation, and then we have a solution that works pretty well. By the way, this must remind you of Michaelis-Menten model. It's very commonly used in bacterial growth or bacteria-mediated degradation or production of products. Okay, if we look at simple reactants reacting together and forming products, the most commonly seen ones in environmental processes are first order, zero order, and second order. So, to summarize, we have zero order, first order, and second order processes. How does a zero order process looks like? Zero order process is independent of the concentration of the compound. For example, if you are looking at production of C compound and capital C gives its concentration at any given time, dC by dt is independent of C. So, any constant here may be or not, but C to the power 0. It is independent of C, it does not depend upon C. Since the C to the power is 0, it is known as the zeroth order. In the first order, dC by dt, rate at which the C is changing with time, is proportional to C to the power 1. And since 1 is the power, it is known as the first order. And in the second order, we have C to the power 2. So, you can have nth order systems too. In case of chemical reaction, this is very important to know. Now, it must also remind you of something else. We started today's lecture by looking at reactants transforming into products, and we saw that the rate at which forward and backward reaction happen is equal to product of the reactants to raised to the power stoichiometric coefficient and product of the products raised to the power of stoichiometric coefficients. So, if here we are seeing that in the second order reaction, C is raised to the power 2 in the rate reaction, what it tells you is that it looks something like this: 2C plus maybe something else gives you the product you are looking for. So, 2 is the stoichiometric coefficient, and in this case 1 is the stoichiometric coefficient. In this case, C does not even show up in the chemical reaction. Okay. This happens typically when the substrate is extremely high. Otherwise, it does not make sense, right? Because if something is reacting, C is transforming into something else, C should show up in the reaction. So, for example, let us say C plus X gives us some products, but C is so high in concentration that you can assume C to be constant. So, just to clarify zeroth order, so let us say C plus X gives me a product P. If you are interested in the rate at which C is disappearing over time, dC by dt, so backward reaction is ignorable in this case, then this will be proportional to product of C molarity, X molarity raised to the power of stoichiometric coefficients, which in this case is 1. Now, let us say C is present in abundance. For example, the nitrogen gas in our atmosphere is present in abundance. If I have a small reaction happening at a corner of a garden that is consuming nitrogen, it is not going to make a big dent in the concentration of nitrogen in atmosphere. So, what I am saying here is that the concentration of C is constant. So, let us say it is constant and it is equal to alpha. I should not have chosen alpha, but let us stick with alpha now. So, I can say dC by dt is proportional to concentration of C, which is almost constant throughout, alpha into concentration of X. So, I can say that dC by dt, the rate at which it is changing, is equal to some proportionality constant alpha X. It is not dependent on the concentration of C at any given time. This is a zeroth order reaction. So, originally, if you look at this equation, if you look at our chemical reaction, this is actually a first order reaction because it is proportional to the concentration of compound C. But since C is present in abundance, the first order reaction transforms into zeroth order reaction. Okay, coming back to summarizing, so we have zeroth order reaction, first order reaction, second order reaction. Okay, the governing equation in the zeroth order reaction would be dC by dt is equal to minus some kind of constant, maybe multiplied with other products, like in previous slide we had multiplied with concentration of X, which is not always the case. So for example, if C is automatically turning into product P, then X will not exist, it will be a constant. In case of first order, it will be dC by dt is equal to minus Kc. In second order, it will be dC by dt is equal to minus Kc square. Now this is very important to know, because let's say I give you a system and I say, hey, compound A is degrading following a second order kinetic. You should know, when you add this into your mass balance, into your material balance, and you're conserving your compound A, you should know what should be the power of A. It will also tell you what should be the units of the proportionality constants. So for units, remember LHS should always equal to RHS. So basically here on LHS, the concentration is mass per volume per time. So on RHS also it should be mass per volume per time for all these three scenarios. So the K units will change. Alrighty, so this is a governing equation. Mass removal rates looks like this. Now this is a clear subsequence of what we have already written. Here it will be Vk, here it will be Vkc, and here it will be Vkc square. So basically just multiplied with volume. The concentration profile over time will look like so. C is equal to initial minus Kt, because again not related to the concentration. Here we get into exponent. This is after you integrate, okay? So C to the power e to the minus Kt. I'm using a minus sign here. It doesn't have to be a minus, but remember we have discussed this in the previous lectures. The minus sign indicates degradation or decay. Alright. So if you integrate this, we get something like this. If you integrate this, we get something like this. C is equal to C naught 1 plus K C naught T. Typically this kind of equations, writing it down, helps people who are not very strong in maths but still want to learn. Okay, now let's look at half-life. So I will not ask you to cram this for the exam, but this is for your own clarification. Something definitely you want to take notes as you're listening to the lecture, because this will help embed it in your brain. Let's say you're writing an exam and I tell you it's a first order reaction, this is the half-life, what is the decay constant, or this is the decay constant, what is the half-life, or when will the concentration become 1/4 of the original. So in these cases it is helpful to know what the half-life in case of 0th, 1st and 2nd order looks like. In 0th order it will look like C by 2K, very simple. In first order it looks like 1 by 1.44K. Here it looks like 1 by Kc naught. Now remember one thing, you don't have to cram these, you can derive each one of them. In fact, I have never crammed these. Every time I have to solve a problem, I derive it from scratch. Okay, so let's look at photolysis. As we know, photolysis is basically when the light causes the lysis or breakdown of compounds. So we might be interested in an organic compound that breaks down under light, or we might be interested in light mediated reactions, for example photosynthesis, where the sunlight actually mediates production of glucose. So in both cases, light is the mediating factor. Light is giving the energy for either the breakdown of compound or for production of the compound. Now how do we model photolysis? In environmental engineering, we are typically not very interested in photosynthesis. It is obviously part of our ecosystem and we want to conserve it, and the trees and the plants that undergo photosynthesis. But we are very interested in photolysis of chemical compounds which are otherwise recalcitrant, which means they don't decay very quickly by themselves, or which are chemically, physically poisonous for the ecosystem. So photolysis, in the examples I'm going to give right now, are going to be focusing on degradation of compounds because of exposure to sunlight. So direct photolysis is typically modeled as a first order reaction. Typically it's a first order reaction. So if you remember from previous slide, first order reaction means the rate at which the concentration of a compound will change will be proportional to the concentration itself. So dP by dt, rate of photolysis, rate of degradation of a compound, will be proportional to the concentration of the compound itself. So you can add a proportionality constant. Now this is proportionality constant for photolysis reaction. You can add a proportionality constant Kp. P is to signify that this is happening due to C, sorry, due to due to light. So let's say in this case our reaction looks like this, C turning into P due to light. The rate at which P is being formed is proportional to the concentration of C. Now this is in case of direct photolysis. Okay, so direct photolysis is when the light is directly hitting the compound C and directly transforming it into P product. It could be degradation or generation of new compound, whatever. And it depends now, Kp, let's look at Kp. Now Kp depends on different things. Kp depends on light intensity, and you have to determine it experimentally. Okay, now let's look at how this rate equation changes when we are looking at an environmental situation where the light is getting filtered out. So let's say we have a lake. So this is the surface of the lake, and the light is hitting it. Some of the light is getting filtered out. Some of the light is able to enter deep into the lake, faint light, and now of course as it goes down the intensity of the light goes down, and we are interested in photosynthetic reactions that are happening in the lake or photolysis, photodegradation that's happening in the lake of a given compound. We need to account that light towards the bottom layers is going to be much more dim compared to the light at the top layers of the lake. So in this situation what we can do is we can focus on what is the average photolysis reaction rate constant, and so let's say Kps. Kps is photolysis reaction rate constant as seen here at the surface. S is signifying surface. Remember, photolysis is still first order, so it is still proportional to the concentration of the compound reactant that we are interested in. At surface, its dP by dt is going to be maximum because of maximum exposure to light. So Kps is the proportionality constant at surface, and we are interested in finding out depth average proportionality constant. Now if you remember, I told you that Kp depends upon the light intensity. As you go deeper in the lake, Kp will reduce. So I know that Kps is maximum. Go 10 centimeter down, the new Kp, Kp10 is going to be lower and different, and so on, Kp20 and so on until the bottom of the lake or bottom of the water body. So what I want to do is I want to find out a depth average proportionality constant which averages the proportionality constants from Kps all the way to Kpb, B being the bottom. So we know that Kpa, which is depth average proportionality constant, will be equal to the maximum photolysis constant which is at the surface, Kp as I naught, which is the intensity of the light at the surface, divided by IO I dash, which is how the intensity is changing, so it is lesser intensity, multiplied by RDF divided by RDF naught. Now RDF is a new term, right? RDF is radiance distribution factor. And what will happen is that RDF by RDF naught typically ranges from 1.2 to 1.6, this ratio RDF by RDF naught. And then again this has to be determined experimentally, and then 1 minus e to the power minus ke lambda max d divided by k lambda max d. K is a constant. This is the equation we use, and ke lambda max is this thing, ke lambda max is known as light attenuation coefficient. So light attenuation coefficient Ke lambda max tells me how the intensity will change with depth, and capital D here is the depth. Again, students, let me remind you, I do not require you to remember all these formula. In the test, in the quizzes, in the exam, you will get a list of all the formula that are needed to write, to solve your questions. What is important, what's the take home message here is that photolysis is a first order reaction rate, and the reaction constant Kp depends upon the light intensity. So if your light is changing, for example, as light moves down the water body, the intensity of light will change, and it will depend upon the intensity of light at the top and how it is changing. It will depend upon the Kps, which is Kp at surface. It will depend upon the radiance distribution factor. This ratio ranges from 1.2 to 1.6. It will also depend upon light attenuation factor coefficient, which is Ke lambda max, and D. D is the depth of the lake. Now, this is in case of lake. What if we are looking at different scenarios? What if we are looking at how light travels through different layers of atmosphere and how that will affect the photolysis of a given contaminant in the atmosphere? So, again, the equation might be different, and we might have to write according to the system. We might have to empirically determine how Kp is changing over depth, over time. But the take home message is photolysis is a first order reaction. The proportionality constant changes with the intensity of light. So if you know how intensity of light is changing, you can use that to find out how Kp is changing, how photolysis constant is changing. Okay, the next thing I want to look at very quickly to end this lecture is biotransformation. Biotransformation is another kind of reactive processes that we see in environment, and someone who works with environmental microbiology, I'm very interested in biotransformation. Now, biotransformation can be in either way. It can include biodegradation, where things are being degraded by biological entities like bacteria and fungi and other organisms, or it could be accumulation of compounds because of biological phenomena. For example, methanogenic bacteria are actually making methane, so they are transforming the organics into methane, into natural gas, which is a kind of biodegradation we are very interested in. Okay, now with biotransformation, when we put a new compound in the environment, the bacteria take some time to get acclimated to the change in the environment, to introduction of this new compound. Once the bacteria have been acclimated, adjusted to the change in the environment, to the new compound, to the xenobiotic, then the organisms that are transforming the compound, that are causing the biotransformation, driving the biotransformation, will use enzymes to do the process of biotransformation. As a result, the equations we use for biotransformation will actually resemble completely the enzyme mediated reactions that we saw here. The enzyme mediated reaction where the enzyme plus substrate will form a complex, and then enzyme and product. So most of the biotransformation processes will have a very similar equation to Michaelis-Menten model. And then depending upon the relative concentration of S and Km, we can convert it either like so or into a first order reaction, first or second order reaction, right? Okay, so this is all for today's lecture. We have covered zeroth, first and second order reactions. We have covered enzyme mediated reactions. We went through photolysis, which is a first order reaction, and then we looked at biotransformation. And let me just end by writing here that this is also a case of enzyme mediated reaction. So we'll use a similar equation as covered earlier in the lecture, but this is enzyme mediated reaction after the microorganisms who are driving the biotransformation have acclimated. Alright students, this is all for today's lecture. In the next lecture, we are going to look at how we can model these reactive and non-reactive processes that we have covered so far under given circumstances using material balance, or also popularly known as mass balance. Thank you. See you in the next lecture.